Society for the Advancement of Creation Science here at Mississippi State University. We're an organization dedicated to studying the interaction between the Bible and science. And periodically we invite guests in to speak on subjects, sometimes specific to biblical history, sometimes focusing on a scientific discipline specifically. Our guest tonight has a broad area of interest that he has contributed to, both in geological sciences, biological sciences. This afternoon we heard a talk on cosmological arguments, and tonight he's going to be discussing some issues related to evidence for global flood. His name is Dr. John Baumgardner. He was a scientist at Los Alamos National Laboratory for more than 25 years. 20 years and is retired. During that time, he has developed a lot of software code used to evaluate ideas, hypotheses that have been generated, addressing the question of how could Noah's flood have occurred. So he'll be discussing some of those things tonight. But it's a special treat for one of the members of our group, Hee-Chin Cho. Dr. Baumgardner is his advisor. So Hee-Chin is working on a PhD degree, and he just finished his qualifying examination and went through quite a rigorous test this last week. And Dr. Baumgardner is one of his advisors. So it's a special privilege for us to have Dr. Baumgardner in to talk. And I love to share it both with the campus, and then we're trying a live stream of this event tonight. So it will be broadcast live, and then it will be available for viewing afterward. So, Dr. Baumgardner?
Denver. It's a delight for me to be back here at Mississippi State. I appreciate Mark Horstmeyer, who I've been a good friend with for, I don't know, probably 25 years. And we got to know each other while I was at Los Alamos and he was at Sandia in Livermore. And so it's exciting to see all the students that he has advised, and many of whom have gone on to bigger and better things. Anyway, tonight my topic, as Denver said, is the Genesis flood. And it is a topic I've worked on for almost 40 years, actually. And so I'll share some of the computational results and other insights I've gotten along the way. Now, why do most people today regard the flood as merely a quaint myth instead of as an authentic part of Earth history? Do you have any thought as to how that's happened? The flood was regarded as genuine history throughout the Western world up to about 300 years ago. So what has changed? What has happened? What has taken place to change that situation? Well, I would point to a development in Europe, often referred to as the Enlightenment, that occurred in the latter half, basically, of the 18th century. And as far as the events in the Enlightenment, James Hutton is an example of someone very much involved in the Enlightenment circles, actually in Scotland. And he today, because of his writings, is regarded as the founder of modern geology. Why? Because he introduced, for the first time, as far as being widely noticed in intellectual circles, the concepts of uniformitarianism and deep time in his book in 1795 entitled Theory of the Earth. Now, a famous quote in that book that gives you a picture of his outlook, is no vestige of a beginning, no prospect of an end, as he looked at the rock formations of the earth. He imagined modern-day processes acting at approximately modern-day rates, acting continuously over a vast span of time. And as he looked at the record and considered that picture, that understanding of the way the earth works, he said it's almost impossible to find a beginning. And basically since the Enlightenment movement was primarily an atheist movement, and those that outlook on Earth history was foundational to point right here, this its erosional boundary marks that what's called a great unconformity in central Wisconsin. And these are giant quartzite boulders, and they have been ripped up from what's underneath the so-called Baraboo Formation, of massive quartzite. So the water, the level of catastrophism that has the water ripping up boulders of this size from this layer and transporting them horizontally for hundreds of miles. And I'm going to argue we find this layer, it's a global layer. We find rocks just like this in the Grand Canyon, is speaking of just mind-blowing catastrophism. This is another shot that makes showing a little clearer this erosional boundary and these huge boulders above it. Okay. Now this same boundary, Precambrian or Cambrian boundary, is very clear in the western United States and in the Grand Canyon itself. And so this boundary between these layered sediments and crystal and rock is beneath all these layers here in this part of the United States. And so these layers are fossil bearing, laterally extensive for hundreds to thousands of miles. And this boundary, right above this boundary, is an extreme erosional discontinuity. And this can be seen easily from the rim of the canyon. Once you start to recognize it, this is the Cambrian to peat sandstone, forms a cliff, and you can, standing on the south rim, you can track that layer from one horizon to the other. Over the entire length of the Grand Canyon, that layer is easily visible. And so this is the great unconformity as seen in the Grand Canyon. This is on a trail from the south rim, the Hance Trail that goes down to the river. And this is that boundary there in the Grand Canyon. In this case, there are sediments at that boundary, and this is a layer of shale called the Hackatai Shale below. But notice the size of these cobbles, these boulders, just right above this boundary. Even though it's referred to as a sandstone, at the bottom of that sandstone layer are these big boulders. In this case, they're quartzite, and they're purplish quartzite, just like in Wisconsin. In this case, it's the Shunumo quartzite. But again, pointing to catastrophic conditions. And here is a boulder of this Shunumo quartzite right here in the Tapeat sandstone. Again, this is the discontinuity right here. This boulder's, and it's about 15 feet in diameter. It weighs 200 tons. And to imagine a water process moving material like this is speaking of just unimaginable catastrophism. All right, we looked at the beginning of the cataclysm. What about the end of the cataclysm? Is there any way to get an idea where in the record the end of this cataclysm is? Well, after so vast amount of sediment had been carried onto the continents and deposited in these horizontally extensive layers, a significant fraction of that sediment was subsequently stripped away from the continent interiors and carried off by runoff water to the continental shelves at the end of the flood. And this is, if you have eyes to see, eyes to recognize it, there's evidence that these layers were laterally extensive hundreds of miles further south originally. That these layers were all deposited like this down into central Arizona. And something happened that subsequent to when they were deposited that stripped all this material away. It turns out that this Kaibab limestone right here, which is at the rim of the Grand Canyon, was resistant, and it was mostly in Arizona at least, it was mostly these layers above that point that were eroded away. But over the continents as a whole, in New Mexico, where I live, for example, we see the same kind of evidence of sheet erosion, just incredible volumes of sediment stripped away. It's especially evident from the air as you look at the topography. You can see a similar style of erosion, massive erosion having taken place. So this would have taken place at the end of the flood as the waters were running off of the continents. So in summary, a staggering amount of geological change took place during this global cataclysm. And the Bible reveals that it all unfolded within the span of only a single year. So what then is the correct interpretation of the fossil record? Is it the record of some 580 million years of evolution? Or is it tangible documentation of the destruction of life by the flood during a single year? Which is it? Well, certainly in all our textbooks, in all our university geology and biology courses, it's claimed to be the former. But I'm saying that there's evidence that that's not the correct story, not the correct interpretation. Some of you, I'm sure, are thinking, well, I've been taught all my life that the fossil record spans hundreds of millions of years. What about the radioisotope methods that consistently yield such vast ages for the Earth's rocks? Well, this indeed is a crucial issue, and it was addressed in a serious way by the Radioisotopes in the Age of the Earth initiative, which spanned 8 years from 1997 to 2005. This research documented multiple lines of radioisotope evidence which limit the Earth's age to about 6,000 years. That's a whole talk unto itself. I can't give it tonight. I was part of that team, and we produced an 800-page technical report, which is online, available free. Each chapter is a separate PDF file if you care to look at it and see these lines of evidence that indicate the Earth is young after all, based on radioisotopes. Okay. But in addition to radioisotope evidence, we have mounting evidence of soft tissue preservation in fossils. And a notable example was published 11 years ago in Science, evidence that dinosaur burial was recent. The author Mary Schweitzer showed well-preserved flexible blood vessels containing red blood cells in Tyrannosaurus rex bone, dinosaur bone, from a dinosaur recovered in Montana. And so she in a video, she showed just how flexible these blood vessels are, which she obtained by dissolving the bone matrix away. And inside the blood vessels are red blood cells like you see here. And this finding has been repeated. Now, several dozen examples of soft tissue from animals whose conventional dates are tens of millions of years. In this case, it was 65 million years. And other dinosaurs, and not only in bones, in the horns of some of these dinosaurs, Triceratops horn, flexible, soft tissue with flexible soft tissue. So it's unthinkable that you can preserve soft tissue for millions of years, especially in an environment like Montana, which have warm summer temperatures. You know, these dinosaur bones are just in the soil, not too far down from the surface, and it's just unthinkable that could be preserved for millions of years. It's amazing this was preserved even for a few thousand years. Okay, so a key issue with regard to the flood: if the Bible is true concerning the reality of the flood, physically, how could so much change occur in the span of only a single year? What conceivably could have been the main causal mechanism? So at this point, I want to start addressing that issue. What kind of mechanism could have caused a catastrophe of this magnitude? In the Bible, it was only about 4,000, 4,500, let's just say 4,500 years ago. So it's in the recent past, this kind of cataclysm. So what kind of mechanism? Well, some major clues to the answer come from the ocean bottom. And a huge discovery made in the 1960s is that all of today's ocean crust is younger than much of the fossil-bearing sediment record that we've been looking at on the continents. So all of the ocean floor today is what has been formed more recently than much of the fossil-bearing sediment record. And so what does that imply? Well, let me just elaborate on that. So again, to repeat, all the ocean crust on Earth today has formed since the point marked by the arrow here. This arrow, basically everything, all the fossil-bearing sediments below that mark, all the layers exposed in the Grand Canyon were already deposited on the continents before any of the modern ocean floor had formed at a mid-ocean ridge by seafloor spreading. So what that means, to say it in another way, is that all of today's basaltic ocean crust has formed since the onset of the flood. And so what that implies is that the opening of the entire Atlantic Ocean, as well as all the other oceans, the opening of the entire Atlantic Ocean occurred during the flood, and it also implies that the continents have migrated by thousands of miles during the flood in only a few months' time. So this is implying that the flood, in addition to being a hydrological cataclysm, was also a tectonic cataclysm. That plate tectonics, a lot of plate tectonics occurred during the flood, that the flood itself was a tectonic catastrophe. What about then about the pre-ocean floor, the pre-flood ocean floor? Well, it's missing from the Earth's surface today, entirely missing. Taking cues from today's seafloor, it must have been recycled into the Earth's interior during the flood. Now, I actually came to become aware of this back in the spring of 1978. It was an epiphany I had as I was trying to understand how plate tectonics might fit with the flood of the Bible. And I went through this process of realizing the present-day ocean floor is young relative to the fossil record, and therefore the ocean floor must have formed during the flood. So this, the idea, the conclusion that rapid, large-scale tectonic changes must have been a fundamental aspect of the Genesis flood, that concept has now come to be known as catastrophic plate tectonics. And the first formal paper, first presentation on this idea was in 1986 at the first International Conference on Creationism in Pittsburgh. So this, so actually that was a paper I presented, and so So I'm connected with the origin of this concept. But, you know, it's something that I believe the Spirit of God gave me there in 1978. So such large-scale tectonic change at the Earth's surface implies that the Earth's interior also was involved. These large slabs of ocean floor are plunging into the Earth. Hot rock is rising up at the mid-ocean ridges, and new ocean floor is forming there. So there's definitely flow going on inside the Earth to allow this kind of catastrophe to happen. So let's review some basics of the Earth's structure. You can basically divide the Earth up into two regions based on the type of material. You've got a core that's about a little more than half the Earth's radius. It is the core, mostly iron. The outer part is liquid iron. And the outer part of the Earth is rock, silicate rock. And it's most of it is referred to as the mantle. And then there is a weak layer at the top of the mantle called the asthenosphere. And then above that is a cold layer, rigid layer, mechanically rigid layer known as the lithosphere. And so the tectonic plates are pieces of lithosphere. The lithosphere represents a mosaic of plates that are able to slide over the Earth's surface because of this weak layer, the asthenosphere, that's beneath the lithosphere. Okay, so that's just a real quick crash course in Earth structure. A little more detail here as to, well, maybe I should back up and point out that here we see some of the Pacific Ocean plate plunging into the Earth's interior. And here we see some continent that is staying at the Earth's surface. There's the continents represent a layer of buoyant material, granitic, basically of granitic composition, and the granite has a lower density than the underlying mantle rock, so it causes the continents to float and makes these areas where this layer of continental crust exists unsinkable. It's so buoyant. So these continents are sort of like icebergs floating in a denser layer of rock, denser material of rock below. So again, so it represents a mid-ocean ridge, where as these plates are moving apart, new hot material rises up, fills the gap. So a little bit of melting here, producing a layer of crust, of basalt that forms the top about 7 kilometers of the ocean floor, ocean bottom. So where that new crust is forming, new ocean plate is forming, is along these mid-ocean ridges. And where the plates are plunging into the Earth, it's where we have most of the Earth's earthquakes. Most of the earthquakes in the world occur where these plates plunge into the Earth. These plates carry down water, which when it gets down here, comes out of the plate, and the water reduces the melting temperature of rock. And so we typically have volcanic activity where these plates are subducting. And so typically adjacent to the trenches, the subduction zones, we have a ring of volcanoes. And there's a lot of plates. Most of the plates are subducting around the perimeter of the Pacific. And so that perimeter is also known as the Ring of Fire because of all the volcanoes around the Pacific Rim. And I might also point out that ocean plate, because of its lower temperature, because it's colder than the rock below, colder than the rock in the asthenosphere, but essentially the same chemical composition, it means its density is higher, and it therefore has a natural tendency to sink. So it allows these cold slabs to sink. It makes it physically possible. The low temperature and higher density makes it physically possible for these slabs to sink into the Earth's interior. And this is a close-up of one of these spreading ridges where a new ocean crust is forming, where the plates are moving apart. And we see this as a blow up of this region. We have a little bit of melting below, basaltic magma coming up into the cracks, freezing, and producing new plate. And we have high heat flow in these regions, so that gives you an idea of what's going on at a mid-ocean ridge. So catastrophic plate tectonics is similar to conventional plate tectonics, except the plate velocities are about 1 billion times higher. So if you just run the numbers, you find that during the flood, if all this new ocean floor forms during those few months of the flood, the plate velocity have to be on the order of 5 miles per hour instead of 2 inches per year as they are today, roughly. So how is this possible? How could the plate velocities be 1 billion times higher? Well, laboratory experiments show that mantle rock weakens dramatically under stress, at stress levels that can exist in the Earth. In a planet with the mass and the gravity field of the Earth, stresses of that magnitude can occur, and this weakening provides the potential for a runaway catastrophe, for these plates to sink catastrophically fast because the mantle weakens as the stresses get high enough. So let's consider another issue. I've already given you some inkling of it, but just how much continental motion occurred during the flood. Well, these following images summarize just how much the continents moved since the time when a supercontinent known as Pangaea existed. So let's take a look. This is Pangaea in what is known as the early Triassic time. And so if we just move forward in time, you see how that Pangaea split apart and the continents move from their positions to their current positions. Let me just run that backwards. Run it forwards again. Idea here. So we're having this much plate motion, this much seafloor spreading and subduction unfold in just a few months' time during the flood. So that's catastrophic plate tectonics. And so again, we base the timing on all of this basically because fossils are indicative of the layers that were deposited in the flood, and we can cue off the presence of fossils to come to this conclusion. So catastrophic plate tectonics, like conventional plate tectonics, accounts for many of the Earth's physical features, including mid-ocean ridges, the deep ocean trenches, the global distribution of earthquakes, volcanism adjacent to the trenches where the plates are plunging into the Earth. So again, it accounts for seafloor spreading, subduction. It accounts for the fact that most of the world's earthquakes, here these were magnitude 4.5 or greater earthquakes that occurred between 1980 and 1995. You see, most of them are next to subduction zones, are spreading ridges. Subduction zones on the west coast of South America, Central America, Aleutians, West Pacific, Java Trench, and so on. There are quite a few earthquakes in the mountain belts, in the Himalayas, for example, which are not actually, they're former subduction zones. Okay. So anyway, the catastrophic plate tectonics, like conventional plate tectonics, predicts this sort of thing. In addition, it predicts that we see the location of the world's active volcanoes, this so-called Pacific Ring of Fire, next to these subduction zones in the Pacific. But there are some geological processes distinctive for catastrophic plate tectonics that you would not expect from conventional plate tectonics. Let's look at some of those. One is that this plate spreading so fast, you'd expect supersonic steam jets emerging from the seafloor along the 60,000 kilometer or 40,000 mile long zone of mid-ocean rift. In addition, associated with those steam jets, you would expect intense global rain from entrained ocean water lofted above the Earth by the steam jets. As the steam jets come ripping up through the ocean layer of water, they entrain some of that liquid water and carry it high up into the stratosphere, and that water that's carried up then falls back to the Earth as rain, as heavy rain. So this is an attempt to illustrate that when you have the plates spreading very rapidly, you have a lot more hot magma in contact with seawater, producing supercritical water. It flashes almost instantly to steam, high velocity steam, which comes out, rips through the ocean layer, entraining water, and these jets go up, carry water up into the stratosphere, which falls back to the Earth as torrential rain. In addition, we would expect giant tsunamis, much bigger tsunamis than we have today. The tsunamis today, most of them are generated around the Pacific as a result of earthquakes. There's some big tsunamis. There's one that struck Indonesia from an earthquake, I think that was in 2004 in the Java Trench. And then in 2011, the big earthquake off the east coast of Japan, the one that destroyed the Fukushima reactors. That was also a subduction earthquake that generated a large tsunami. But with plate velocities this high, we'd expect much larger tsunamis and more frequent tsunamis. So that's going to be a major aspect of the cataclysm, tsunamis generated by these rapidly subducting plates. In addition, significant up and down motions of the Earth's surface because of the rapid flow of rock inside the Earth, and then a dramatic uplift of today's mountains at the end of the cataclysm, and then an ice age following the flood. So let me say a little more. This shows how tsunamis are generated. That if this zone is stuck here, if the plates are stuck, the stresses build up. This plate is deformed, is shortened, and buckled upward. And then if that locked fault unlocks and suddenly releases, this plate rebounds and pushes up a mound of water, which becomes a tsunami. Then a result of all the subduction and so on, in regions where the crust was thickened, at the end of the flood, that thickened crust is going to rise, bob up like a cork, and reach its equilibrium level and generally punch up mountain belts. So all of today's mountain belts rose recently and suddenly. And that's something the conventional theory can't explain. The sudden recent uplift of all the high mountains in the world today, including the Andes and the Alps, the Himalayas. So we get a sudden uplift of these mountains after the cataclysm. And then the warming of the oceans during the flood led to high rates of evaporation, precipitation, and a rapid buildup of polar ice sheets and mountain glaciers following the flood. So this flood catastrophe naturally predicts an ice age afterward, which, and so we believe the ice age followed the flood immediately. For the 2 or 3 centuries after the flood was the time of the ice age. So a crucial issue in all of this, I'm should be finishing up here, but I want to talk about the mechanism here and address this issue. How can ocean plate actually sink vertically through it's actually about 1,800 miles of mantle rock in a few months' time? So basically, so what we have happen is these ocean plates need to sink at rates of meters per second to the bottom of the mantle. So and it's possible, I'm going to argue, because the mantle rock weakens when it's under stress. Now, the properties, the deformation properties of rock have been measured in labs all over the world for the past 50 years in apparatuses in earlier years like this. This is this is an oven that controls the temperature. Stress is applied to a sample in the middle of this oven by these silica rods, and they can measure they measure the amount of stress applied to the sample and the rate that the bars compress it. And then afterward, they can take the sample out, look at the sample under an electron microscope, look at how it's deformed, and actually they can, the electron microscope can see how planes of atoms have slid over one another like a deck of cards, so that these deformations can be studied. So this has been going on for the last 40 to 50 years. So silicate materials have been relatively well studied, well documented. And from these experiments, they've been able to draw maps like this of the deformation properties of silicate minerals. This is too complicated to explain in detail, but I will say that the rates of deformation along this line, which represents 80% of the melting temperature, it shows that for relatively modest changes in the level of stress, the deformation rate can change by more than a factor of 1 billion. And that's been documented in laboratory experiments. So that's that's something that it can be checked in the laboratory. Now, so I'm going to show you here a 2D computer calculation using the deformation properties that are reflected in that previous graph. And this calculation showed that the rock material can fail catastrophically, can weaken so that a runaway catastrophe unfolds. So this is a simple little 2D box. The thickness, the height of the box corresponds to the thickness of the Earth's mantle. The colors denote temperature, and the arrows denote the velocities. And so I'm taking a few snapshots out of that movie that shows how the material suddenly plunges to the bottom. The hot material rises rapidly to the surface at speeds on the order of a few meters per second, which is what is needed for this cataclysm to unfold in the Earth in a few weeks' time. And so this motion is driven simply by the gravitational potential energy in the cold material at the top and the hot material at the bottom, simply from the initial temperature differences. So this is a little animation of that calculation. It's relatively simple. It requires some very sophisticated numerical techniques to be able to handle the very strong variations in physical properties that unfold during this calculation. But it does demonstrate that the physics works. So although it may not seem that complex or impressive, it demonstrates the physics indeed works, specifically that stress weakening in rocks can produce catastrophic consequences in a planet with the gravity field of the Earth. Now, I did my PhD dissertation in developing a 3D computer model of the Earth's interior to be able to do these kinds of calculations. This was back in the early 1980s. And so this is a cutaway view of the computational grid that I developed and that I continue to use. This is in this case, the spherical shell representing the Earth's mantle has been chopped up into about 1.35 million cells, small little cells like this. And so I solved the conservation equations of mass, momentum, and energy in each one of the cells, use a big computer to solve those equations, and can track the flow of material inside a planet like the Earth. So I'm going to show a calculation. This shows one reconstruction of Pangaea. And so I'm going to start the calculation not at the beginning of the flood, but when Pangaea existed, because I have a little better handle on a good initial condition. It's not easy to know what the initial condition was further back, but we have enough ocean floor data to know what that initial condition might have looked like. So that's where I start this calculation. So this is my reconstruction of Pangaea. You can see the present continents back in their Pangaean, approximately their Pangaea locations. I put a ring of cold material around this supercontinent, plus some cold material out here in what is now Southeast Asia, running down into Australia. So I need that to provide some initial forces to get this calculation going, to get it to move. So this is a slice through the equator showing that this cold material, which is 400 degrees colder than the surrounding material, it only penetrates down 400 kilometers. So just with this relatively small initial perturbation, I'm able to get material start to moving. It'd be nice if I knew what the actual temperature distribution inside the Earth was at that point in its history, but I don't. So I'm guessing. I'm using a guess that there was cold material around the margins of that supercontinent, and I have good reasons for guessing that. So anyway, I just start solving those conservation equations, letting the calculation go, and one thing that is surprising is that with that type of initial condition, these blocks move apart approximately the way we know from the seafloor data that the continents did move apart, the plates did move apart. So it's just an attempt to try to get some idea, get some clues, get some more insight, understanding of that process. So that was, I'm going to show you, now this is the view from the slice through the equator. And you see that cold material that's plunging down in those subduction zones, coming down and coming down to the boundary between the mantle and the core, and spreading out and pushing the hot material aside, okay, in that 3D calculation. So this is, that was a view, cross-section. This is a view from the North Pole of that same calculation. And you see surface velocities on the order of a meter per second. Here, okay. This is a view from the South Pole, showing and basically South America is going in roughly the right direction, Antarctica in the right direction, Australia in the right direction, to take it over here, India and Africa also going roughly in the right directions. So it's just a crude attempt to try to see if I can model that kind of behavior. And indeed, you know, it seems to hang together. Now this is an animation showing sea level and how the sea level changes during the course of all of this. The purple line is the sea level, and I have actually around some of these mid-ocean ridges, those actually get above sea level in this particular model. I think I need to adjust some things, but on the other hand, the continents do get flooded with water. Here's the area inside this purple contour is below sea level. So most of the continents do get flooded with the dynamics that unfold during this calculation. So is there evidence supporting a recent episode of catastrophic plate tectonics? Is there any signature of that in the Earth? Well, the answer, I'm pleased to say yes. Seismic images of the mantle reveal a ring of unexpectedly cold rock at the bottom of the mantle, beneath the subduction zones that surround the Pacific Ocean. And this is a view attempting to show the density variations inside the mantle. It's this using seismic data. The process is called seismic tomography. It's like medical tomography. Medical tomography uses X-rays. The seismic tomography uses tens of thousands of earthquakes at hundreds of seismic stations around the world, takes all that data, crunches it in a computer, and comes out with the density structure of the inside of the Earth. Actually, it's the seismic wave speed inside the Earth. And where the seismic wave speed is high, it implies cold material. Where it's slow, it implies hot material. And the surprising thing is that the difference between this, all right, so one thing we can see is this is the Pacific Hemisphere, the Atlantic Hemisphere. We see a ring of cold material basically beneath the subduction zones around the Pacific. And in the center, some hot material that appears to have been squeezed up like toothpaste as that cold material settled down to the bottom, just like that 3D calculation was showing. And this, if you look at the eastern hemisphere, you see the same ring that's just viewed from the eastern hemisphere, but another blob of hot material beneath South Africa in the southeastern Atlantic Ocean basin. So it's, the problem is that according to the secular model and the standard dating scheme, according to that scheme, it takes 100 million years for rock from the Earth's surface to sink down through the mantle. And by that time, the rock has warmed up from its surface temperature to near ambient temperature at the bottom. So it was a huge surprise and created all kinds of concern and surprise, and to find such large regions of such cold rock at the bottom of the mantle. The temperature, the implied temperature is very close to the surface temperature that the rock would have at the surface. So it's as if this rock has gotten down to the bottom of the mantle very recently, not had time to warm up to speak of. So I say that this is fairly strong evidence of a recent episode of catastrophic plate tectonics. So again, I want to emphasize that its energy source to drive this cataclysm is nothing more than the gravitational energy, the cold energy, the gravitational potential energy. Let's see if I have something I can use my case for my pointer here. This object has gravitational potential energy relative to the stage here. If I drop it, that gravitational potential energy gets converted to kinetic energy and then into heat when it slams into the floor. So it's the same thing going on. The cold material at the top has gravitational potential energy relative to the base of the mantle, and that's the energy that allows does the work that's involved as that slab sinks to the bottom. So that's where the energy is coming from, and so I want to. This is just a little extra tonight that most audiences have not seen before. I'm going to take an extra 5 minutes on it, but I want to address the question: how were the continents flooded and the sediment record with all its fossils produced? I've only talked about the tectonics. What about the water itself and the sediment and the deposition that produced all these layers we see in the Grand Canyon? And so I'm going to use as a mechanism tsunamis, the tsunamis that arose during this rapid subduction. And again, this is a very similar sequence. So we have the slab plunging into the mantle. If it gets locked, we start deforming the overlying plate, and then it gets deformed even more. And then if this unlocks, you have a sudden rebound, and that pushes up this water that had been in this hole, pushes it up and generates these waves that produce the tsunami and drive a lot of water onto the continent. And so basically, what this model I've developed does is I have in this case, I have two regions out in the ocean. You can call them subduction zones, where about every 4 minutes along a segment, there is a slipping and a tsunami generated. And so overall, every 4 minutes, somewhere in the ocean, I have a tsunami going off. And these tsunamis generate waves, large amplitude waves. And this region over here is the continent. And so it takes about 10 hours for the tsunami generated here to start impinging on the continent. And let's see. So that was after 10 hours. This is a snapshot after 2.5 days and after 5 days. So this is 2.5 days, this is 5 days. This is the continent is centered at 0 longitude. So basically you're looking right down on a circular continent. And so what we have is water basically coming, we start to see a pattern of flow form, a circulating motion like this. Tsunamis impinging all the way around, but because of the Earth's rotation, we start having a circulating water pattern like this. So this is looking at 0 degrees longitude. This is at 90 degrees. So here's where the tsunamis are. So we're seeing these counterclockwise circulations, like a low pressure area out here in the ocean basins. Anyway, there's a circulation pattern that starts to arise because of the Earth's rotation. And later, these are plots after 50 and 100 days when these patterns are well developed. And we have this is the height of the water surface above the original sea level. So here we have water 1,500 meters above sea level. So 1,500 meters is between 4,500 feet and 5,000 feet. So you have a gigantic amount of water. Now, how does this happen? Well, initially the tsunamis put more water onto the continent than can drain off by gravity. So the water level continues to rise until the water is high enough where the rate of runoff equals the rate of emplacement. But in that equilibrium level, according to this calculation, results in major flooding of the continent. And even in these regions, you have several hundred meters. So this is more than 1,000 feet deep, even in these green regions. And okay, so that is the height of the water surface. This is the water depth above the land surface in this plot. And here you can see zones, you can see regions that I've marked at 0 depth. Those are regions that have gotten eroded. So so those are eroded regions. So we have erosions around the margins and regions where where there's a very deep water depth. And these plots represent, let's see, the cumulative bedrock erosion and the instantaneous thickness of suspended sediments. And here at this late time, we have in some regions equivalent of 100 meters or 300 feet of suspended sediment, suspended in the water. So incredible sediment loads are being carried around, moved around. So I need more time. I'm just going to give you a flavor of what these are like. So these are snapshots of 50 and 100 days of the net sediment thickness on the surface. So there are regions that are more than 1,250 meters thick. So that's like 4,000 feet of sediment there in places produced. This is 50 days and this is 100 days. So you have this process able to erode, transport, and deposit thousands of feet of sediment over major portions of the continent. So if you're interested in looking this work up, you can download for free the paper that was published in the Answers Research Journal this year in February in 2016. The title of that paper is Numerical Modeling of the Large-Scale Erosion, Sediment, Transport, and Deposition Processes of the Genesis Flood. So it's just a beginning exploratory calculation, but I believe it shows gives the outline of that process. Okay, so what are the takeaway points of what I've talked about tonight? Well, first, the Bible is emphatically clear about the reality of a catastrophic flood. There's no debate about what the Bible says, right? The physical evidence for the flood is abundant and I claim readily available. Anybody that cares to can go out and check out these deposits, see these formations, see these evidences for rapid geological process. And the third point is the reality of the flood is a rationally defensible proposition. For those who are Christians in the audience, there's no need to be apologetic. The flood can be rationally defended. The evidence today is there to do it. And third, I'm saying defending the flood is essential to upholding the Bible's truthfulness in today's intellectual climate. And so we are in a spiritual war. And there is a ferocious assault on the truthfulness of the Bible. And one of the major points of attack has to do with the early chapters of Genesis and whether there really was a flood. The flood is scoffed at, laughed at. But I say, and the Bible is rejected by many because they believe that the flood is just a myth. But I say the evidence is I don't know how strong to say, overwhelming, but certainly persuasive that the flood is a reality, a historical reality. So I say that what we see today is a fulfillment of this prophecy in 2 Peter chapter 3, where Peter says, in the last days, people will be willfully ignorant of this fact that by the word of God, the heavens existed long ago, and the earth was formed out of water and by water, through which water the world at that time was destroyed, being flooded with water. Peter says in the last days there's going to be scoffers that are claiming all has continued just as it was from the beginning of creation, and that's their justification for rejecting the idea that Jesus is coming back. But when he says that, when they do that, they're being willfully ignorant of the flood. So I say, especially with the evidence we have today, there's no excuse. You have to be willfully ignorant to ignore this evidence. So the flood ought to serve as a warning to this present generation. Jesus gave it as a warning in his generation. Jesus said, just as it happened in the days of Noah, so it will also be in the days of the Son of Man when he returns. They were eating They were drinking, they were marrying, they were being given in marriage until the day that Noah entered the ark and the flood came and took and destroyed them all. He says, so it will be in the day that I return. In Hebrews 11, it says, by faith, Noah, being warned by God about things not yet seen, in reverence prepared an ark for the salvation of his household, by which he condemned the world and became an heir of the righteousness which is according to faith. I believe Noah's faithfulness serves as an example for us. He is a man of faith, and God delivered him. And I believe we need to be faithful as agents of truth, standing for truth, standing up for what God has said in our generation. So I believe Noah's example ought to motivate us to be faithful in communicating the truth that Jesus, to quote 1 Peter 3, Jesus died for sins once for all, the just for the unjust, that he might bring us to God. What a wonderful privilege we have to be able to tell others how they, as a free gift, can be perfectly reconciled with God and have eternal life as a gift. That's a glorious message we have to share with the world. So thank you for your attention tonight. Hope this has been an encouragement to you. I'm open to take questions if anybody has a question. Yes. All right, the question is, you're taking a geology class, I think, but you're not a geology major, and you're being confronted with these ideas, and what should your response be? I would say that's a little tricky. If you're going, it's not a trivial thing to challenge a professor on something like this, especially a inflammatory topic like this. So I basically would say, pray about it. Ask God, does he want you to do something or not? He may not want you to. But at least in your own heart, you've been exposed to this information, and you ought to be somewhat be strengthened where you don't have to be intimidated by those claims. So at a minimum, you need to stand strong. If you need to read the Bible again, read the account of the flood, or look up on a website more of this evidence I've been showing to be more strongly convinced, then that would be good to do. But I believe some students are called to carefully, perhaps not do it during class, but go to the professor privately and share with them some reasons, that ask them if they're aware of certain things, and ask them how do they account for, say, the lateral continuity of the sediment formations. How do they account for how all these fossils could form under very slow sediment deposition rates? Some of these issues that I raised tonight, you could just go and you could say, I attended a talk recently where some of these things were pointed out. I'm curious how you would answer these questions. So that's something that some of you students could do. I would say you probably should not, unless you're really well-grounded, not challenge the professor publicly. That'd be just my advice. Mark might have a little, encourage a little more radical action. Do you have any comment?
geology class, undergraduate, and the last 2 weeks I decided to go to talk to professor, just like you said. And I just asked the questions and this kind of thing. And the last day of class, to his credit, he looked at all this because I went through and I talked to you about all these things, but it's non-introductory, I don't know any of that. And then he said, I thought to his credit, he said that, I'm not sure he would have. I had to go to talk to him like, 2 weeks before that.
Yeah, so I would say, you can, as Christians, we can afford to be generous with other people. We don't have to, beat them over the head, tell them they're idiots, and treat them, as subhuman beings. We're so rich in Christ that we can afford to be generous to other people. And so I would say when you approach a professor, you go with respect, but you can ask them good questions and possibly get them to thinking.
I think for the sake of consistency, mentioned that when I was a boy in church, I asked and he believed in God, he was local. And then, of course, I read my first question to them were, kind of, but what was he told me? It was local flood. And then second, what was he on response to them?
Well, as I was reading those verses from Genesis 6 and Genesis 7, I was trying to emphasize how there's no way that if you handle the text honestly, if you handle that text carefully, that you can possibly get a local flood out of that. And if you sort of just take those early chapters of Genesis at face value, and just assume reasonable reproduction rates and look at especially given the longevity of the people. There was, by the time of the flood, after 1,650 years, there would have been a substantial human population. And people that advocate a local flood generally think in terms of the Mesopotamian Valley. And so, if there was a local flood, why didn't God just tell Noah just to take his family and go, to higher ground, if that's where he was living? The local flood just doesn't make sense. And especially if the human race was scattered over a good fraction of the earth at that point. It's a way. A local flood is a way basically to keep, to accommodate secular geological thinking, and just say, well, it was a local flood that left no evidence.
Well, 30 years ago, he moved to New Mexico and drove up into Las Cruces in the Oregon Mountains, running and that day there were thunderstorms and there was one rainbow after the other. The rainbow was God things. Yeah.
I would say not anytime soon. That catastrophe eliminated all of these large density anomalies that were responsible for that runaway. So those are gone now. So that kind of event can't happen now. The question, everybody, maybe for the sake of the recording, I should repeat the question. The gentleman was saying that he, in southern New Mexico, saw these beautiful rainbows. And I lived in New Mexico, often they're double rainbows. And that was, in the Bible, that was God's promise, never to again destroy the earth with a flood. So the question was, can catastrophic plate tectonics, can another episode of catastrophic plate tectonics occur? My answer was no. those large density anomalies that appear to be responsible are gone. They were eliminated by that flood catastrophe. Other questions? Any other questions?
Real quickly, something you said earlier in your talk kept my attention. Up to about 300 years ago, the flood was considered a historic fact. It was about everybody in the age of the Colonial Enlightenment, and that all got put out the window. I have a rather idealized vision of what science would be, and I understand we have something like that that's accepted for the official, for the accepted position has changed. There needs to be evidence to show why that changed. Was there ever such evidence produced, or is this just something that changed because we understand?
Okay, the question has to do with had to do with my comments about the 300 years ago, even almost to 200 years ago, most people believed in a global flood, like the Bible describes. And the question was, if science proceeds in such a thorough, careful way, was there good reason to give up on the global the global flood? After all, those fossils were still around. I mean, everybody saw these fossils, especially in Western Europe. They were fairly easy to find. My assessment as to why the uniformitarian position gained ground was that as people became more aware of the thickness of these fossil-bearing layers, the depth of the fossil-bearing record, it was almost beyond their comprehension how a single event could possibly have generated so much geological change. So even though there were Christians, they were called scriptural geologists in the first half of the 1800s. There were scriptural geologists continuing to try to defend the biblical flood. They just could not the onslaught of this other viewpoint. And I think it was because they could not provide, they didn't have a mechanism. They could not provide a plausible way for so much geological change to unfold in such a short period of time. So I think that the difference now is, or one thing that changed around 1960 was the advent of plate tectonics and the awareness that processes inside the Earth could produce large-scale changes at the Earth's surface. So it became, I believe, for the first time, really conceivable how if you had some kind of catastrophic process in the mantle, you could drive processes at the Earth's surface that could do what I've described tonight. So just to be a little bit generous to the people back then, the Christians trying to defend the flood in the days of Lyell, they couldn't give back an answer. What kind of process could generate thousands of feet of sedimentary rock with fossils in them in just a few months' time? They could not come back with a good answer. So I would say historically that was part of the problem. And also I would say that the Apostle Peter prophesied that this state of affairs, this rise of uniformitarianism would occur in the last days. And so it was already, God already knew that something like that was going to happen, that would happen. Okay. Any other question? Yes.
I'm just wondering whether what we think of the possibilities for kind of like aftershocks after the flood. They seem to just from based on I guess from maybe mythology or other people's or other nations' historical records. There seem to be a lot of flood stories. Some of them I think are perhaps identifying the flood, but others I'm pretty sure are not identifying the flood, and sometimes they're confused. There is a story in China, for example, about a flood that happens at the beginning of the Shada, which is oftentimes confused with the Great Flood, but I think that happened actually around the Tower of Babel.
Okay.
And so that related also to the Tower of Babel, whether there could have been some, like, basically aftershock, but that's what it is.
Okay. So the question has to do with some after effects of the flood. Later local floods. In my assessment, one of the big things that took place after the flood, well, first of all, I don't believe the earth, as far from a seismological standpoint, became quiet immediately. I believe there were major earthquakes that continued for centuries, and that was one reason people lived in tents or caves, that it didn't make sense to try to build permanent buildings because of the frequency of the earthquakes. And even when they did start building cities, there's record evidences that they were frequently destroyed by earthquakes. Jericho is an example, right there where the earthquakes are very frequent. But I suspect that there were, you use the term aftershock, that there were earthquakes, a lot of earthquakes for the first few centuries after the flood. You mentioned also floods, local floods, fairly severe local floods after the big flood. The main event after the flood was the ice. In my view, was the ice age, and there's evidences of a pulsing of the glaciers, and time and melt back, and so. Certainly when those glaciers started to melt, catastrophes. One of them was the Lake Missoula flood that scoured a significant area in eastern Washington. There was an ice dam that broke Lake Missoula, an ice dam during the end of the Ice Age, holding back this glacial lake, and that dam apparently failed, and that lake emptied out in just a day or two down through eastern Washington into the Columbia River, and produced incredible erosional features. So that's an example of a fairly major flood, catastrophic flood, local flood after the flood. But it was in connection with the Ice Age, the end of the Ice Age. I'd expect in regions adjacent, there could have been a number of events like that. My estimate is around 300 years after the flood. Okay, good question. Okay, well, I think if no one has any more questions, we'll adjourn. I thank you for your attention. And if some of you have some things you want to ask me privately, I'll be here. And otherwise, may God bless you and encourage you. And hopefully this has stimulated your thinking. So good night.